should thank Professor Hitzer for his very kind invitation to ICU. This is, I think, my third time I have been here, so I really appreciate it. So thank you so much. Okay, so I gave this talk. Next week I'm going to give a more technical talk about black holes. But I gave this talk in India when I was there last year, and people liked it a lot. So, because Eckhard asked me to give a talk for the general public, so I decided to choose this talk because, first of all, in many universities at the undergraduate level, special relativity and gravitation is not taught at all. In many universities, I noticed. So I thought that this would be a nice period and a nice occasion to talk a little bit about this, about relativity, gravitation, and black holes. Okay, so let me just begin. Okay, so I'm going to begin briefly by, just describing what the postulates that Albert Einstein proposed in order to formulate his theory of special relativity that later on, 10 years later, gave birth to the general theory of relativity. So I'm going to be speaking about Lorentz transformations, and the physical implications of the Lorentz transformations. In particular, the time dilation and length contraction, and also how the mass depends on the velocity. Also, I'll be talking about space travel, how it will be possible to reach the outer edges of the universe if you were able to build a rocket that endowed you with a perpetual acceleration. Because all of us, since the very day we were born, we experience a world of constant acceleration. So right now, when you're sitting on your desks, you're experiencing the force that the chair exerts on your body. So all of us right now are experiencing a uniform acceleration of gravity, 9.8 meters per second square. So if you could build a spaceship that continuously accelerates all the time, you'll be able to reach the outer skirts of the universe. I mean, it will take quite some time, but much less than we expected. Then I will talk very briefly about the general theory of relativity, and also I'll also talk about black holes and black hole thermodynamics. And I'll talk, and at the very end, I'll talk about the recent advances, and I'll be talking about wormholes and about the Einstein-Rosen connection with the Einstein-Podolsky-Rosen paradox. Okay, so let me just briefly begin with the postulates of Einstein. Einstein postulated his theory of relativity. His first postulate essentially said that all the laws of physics should be must have the same form relative to any inertial observer. So by an inertial observer, you mean an observer who moves with a uniform velocity. So either the observer can remain at rest, or he can move with uniform velocity. So the laws of physics should be invariant or covariant in any frame of reference that is inertial. And the second postulate is that the speed of light is in vacuum is the same for every uniform observer. So as a consequence of that, you see the Lorentz transformations were discovered before Einstein postulated the theory of relativity. And these were transformations that left invariant the Maxwell's equations of electrodynamics. So these are transformations that relate the space-time coordinates in one frame of reference to another. So let me briefly describe what they mean. Suppose you have an observer like us who are fixed at the origin, and we have a ruler in the x direction, we have another ruler in the z direction, and I have another ruler in the y direction, and we also have a clock in our hands, but I cannot draw the temporal direction because we live in 3 dimensions, and it's very hard to draw the 4th dimension. But imagine you have an observer like Alice sitting fixed at the origin with a clock in her hand and a ruler that allows her to measure distances along the x, y, and z direction. So imagine you have Bob, O prime, this is the prime frame of reference, where now Bob is moving along the x direction with a uniform constant velocity v. So this person, you know, has his own rulers and also his own clock. So you want to compare the measurements of Alice compared to the measurements of O prime, or vice versa, the measurements of Bob compared to Alice. Okay, so for the relationship between the coordinates in one frame of reference are given by t prime, and x, t, y, and z are the coordinates in the fixed frame of reference. So these are the relationships that allow me to map how the space-time coordinates in one frame of reference are related to the space-time coordinates in the fixed frame of reference. Okay, so these are called the Lorentz transformations. And this factor of gamma is called the Lorentz dilation factor, that is given by the ratio of 1 divided by the square root of 1 minus the ratio of the velocity square compared to the speed of light. So later we'll see that if the velocity were greater than the speed of light, then you're going to have the square root of a negative number. Okay, and the square root of a negative number, you know, is an imaginary number. So mathematically speaking, this is telling you that the maximum value that v can take, the velocity has to be equal at most the speed of light, because you cannot have this term inside the square root to be negative. So this factor over here is it's always greater or equal to 1, and it's called the Lorentz dilation factor. Okay, so you have a prefactor here. Okay, so notice that these transformations only affect the motion along the direction of motion. So the x and x prime coordinates do experience a transformation, but the transverse coordinates to the direction of motion remain invariant. So the readings of z and z prime are the same, and the readings of y and y prime are the same, because these are transverse coordinates to the direction of motion, which is b. Okay? So now you want to compare the intervals in one frame of reference to the other. So you know, you just take the increment of t prime, for example, will give you this relationship over here. So the increment of t prime is given by the Lorentz dilation factor, by the time interval in the fixed frame of reference. And notice now that how time elapses in one frame of reference now involves how time elapses in the fixed frame of reference, but also it's correlated to the notion of how space, the interval in space. So now what this is telling you is that the notion of space and time is fused with each other. So now you have a unification of space and time, because now x and t intermingle with each other. So on the coordinate transformations, x and time are commingled with each other. Okay, so this tells you how the intervals in the length interval vary in terms of the length intervals in the fixed frame of reference and the length and the time interval, and similar with the other quantities. So what happens if you ask the questions? Okay, this tells me how the prime frame of reference behaves in terms of the unprime frame of reference. So what happens if you take a different perspective and you ask yourself, okay, now from the perspective of Bob who is moving, if I am Bob, relative to me, I am fixed, I'm not moving, but then I see Alice moving backwards. Okay, because if I'm moving to the right relative to O, this means that O is moving to the left relative to me. Okay, so now if you want to write what are the transformations of the fixed frame of reference in terms of the moving frame of reference, the only thing you have to do is change the sign of V, because now V becomes plus V, and the only thing you have to do is replace the primes for unprimes. You replace the primes for unprimes, and the unprime for the primes. So from here, you can go to here by exchanging primes for unprimes, and flipping the sign of the velocity. Okay. So now, what are the physical consequences of this? Okay. So if you look at the first equation, you know. Well, actually, let's look at this one over here. This is the notion of time dilation. Okay. Let's focus on this transformation over here. So let's suppose that you have a clock fixed at a given point, and you let time evolve. So you let time flow along the vertical direction. So this is my clock that remains in the same position in space. Okay, this is x, but the clock remains in the same position in space, and I let time flows. So because the position in space does not change, the increment of x is 0, because along this line over here, I'm not changing the values of x. Okay, so this will be 0. So the only thing that survives is this term over here. So I'll have that the time interval in the moving frame of reference is related to the time interval in the fixed frame of reference, but it has a prefactor of gamma, where gamma is the Lorentz dilation factor, which is greater or equal to 1. So what has happened is that there has been a time dilation, because the factor of gamma is actually greater than 1. So this is called time dilation. So that means that the time intervals in one frame, when you compare it to the time intervals in another frame of reference, they are related by a factor of gamma. So this is called time dilation, because the factor of gamma is greater than 1. Now I'm going to talk about what do I mean by length contraction. You know, let's suppose that I'm looking at this equation over here, okay, and I'm going to measure, for example, I'm going to have a train. Okay, this is the moving frame of reference. I have a train that is moving with a velocity v. And as I approach the station, this is the station, the platform, okay, I'm going to make the measurements of the length of the platform at a given instant of t prime. So I'm going to measure the length of a platform with respect to the moving frame of reference at t prime, at an equal moment of t prime. In other words, I'm going to let the increment of t prime be 0, because I'm going to perform the measurement at simultaneously relative to the person who is moving. So delta of t prime is 0. So in that case, I only have this only survives over here. Okay. So what I have, when you look at the third equation, if I perform a measurement at the same time in my frame of reference, when you look at the third equation over here, you have delta of x is the Lorentz factor delta of x prime. Okay, so from here, you know, you just solve for delta of x prime, and you have is delta of x divided by the Lorentz factor. So there has been a contraction. So this is what we mean over here, a length contraction. So what happens is when you have a train here, if you're moving, the person that is inside the train is going to measure a shorter length of the platform compared to a person who is fixed at the train station. Okay? So this is the phenomenon of length contraction and time dilation. So the immediate physical consequence of this is the following. What do you mean by time dilation, for example? Okay, so here you have a muon, okay, that is created, you know, up in the atmosphere, and after a certain time, relative to its own frame of reference, it decays into a particle. Now, if the muon is moving with respect to an observer on the Earth, because of this time dilation effect, is because of this time dilation, relative to an observer that lives on Earth, he's going to see a dilation of the lifetime of the muon. So the elapsed muon time relative to the person on Earth is being dilated. So the muon can actually is created in the atmosphere, and it can decay, and we can observe it in the laboratory on Earth. Okay, so because otherwise the muon will have lived very shortly and will have not been able to detect the muon. Because remember, the muon lifetime in its own frame of reference is much shorter than the muon lifetime observed for an observer on Earth. Okay. Another way of explaining this picture is from the point of view of the muon. Remember, I talked to you about length contraction. If the muon is moving with a certain velocity, it's coming down very fast. From this point of view, the Himalayas, instead of being 8,000 kilometers, is actually shrunk due to the length contraction. So the Himalayas relative to the muon has been shortened, have been contracted. So for the muon, he has to travel a distance which is much less than would have been traveled relative to an observer on Earth. Okay, so these are the consequences of time dilation or length contraction. Okay. Any questions about this? You know, if I speak too fast, please let me know.
Just one quick one. So that means that the muon speed is close to speed light.
Well, the muon speed has to be very fast, yes, because you see, because remember, you have this factor over here, the Lorentz dilation factor. So these effects are noticeable only when the velocity is what you call relativistic. Because if the velocity is very slow compared to the speed of light, the relativistic effects are negligible and you will never be able to notice them. But of course, yeah, this is what you call relativistic particles.
Does that also mean the velocity of the muon is like constant?
The velocity of the muon,
It does not.
well, the velocity, the muon has a certain mass. Okay, so okay, we know that the speed of light is always constant. The velocity of the muon has a certain velocity. It has a certain mass, of course. So the mass of the muon relative to an observer at rest will increase. Okay, because it's a function of the velocity. I'll talk about that later. But yes, the mass. One thing is rest mass. Another thing is the mass observed by an experimenter. So yeah, so okay, but here you imagine that the friction by the atmosphere is negligible. So the muon essentially that is not slowed down by by the atmosphere. So assume the velocity is constant. Yes.
Oh,
okay. Because of course, if the velocity is not constant, then you have to take into account all these transformations. Because now, if the velocity depends itself on time, then you have to change everything. Okay. That's where general relativity comes to the picture when you look at the geodesic equation in the curved spacetime. Okay. Can I go forward? Okay, and then now if you like pictures, if you have an artistic mind, you can represent those mathematical equations I just wrote down by simply this is the x-axis, for example, and this is the t-axis, and in the prime frame of reference, the x prime axis will look like this line over here, and the t prime axis will look like that. It's when you map one coordinate system to the other, it's like mapping the x prime axis, how does it look with respect to t and x, and the t prime axis, how does it look with respect to t and x. Because remember, I told you that in relativity, the space-time coordinates become mixed, become entangled with each other. Okay, so those transformations that I wrote to you earlier, if you want to draw a picture, this is what they look like. So you can check the time intervals, how they compare in one frame of reference to the other. So there's a time dilation and there's a length contraction. Okay, now another interesting consequence of the Lorentz transformation is the notion of simultaneity. For example, you could have, a train you know, this is Marvis, that's what the name they use. So you can have a train that is moving at a constant velocity with respect to an observer, Stanley. And let's suppose that you have lighting struck at the front of the train and at the back of the train. So from the point of view of Stanley, the lighting strikes at point A and point B at the same time. Okay? But from the point of view of the person who's inside the train, the notion of simultaneity is not an absolute. Because, for example, if there's a separation between the front door and the back door, you know, delta x over here is the separation between the back of the train and the front of the train. If there's a certain distance between the front door and the back door, delta of x is not 0. Okay? Let's suppose that Stanley says, well, the lighting strikes at the same time in the front door and the back door. So relative to him, the delta of t is 0 because the event takes place simultaneously. So he sees the front door and the back door occur at the same time. In other words, the lighting strikes the front door and the back door at the same time relative to him. So delta of t is 0. So this term is 0. However, due that there's a separation between the front door and the back door, delta t prime is not 0. So that means that relative to Marvis, the event is not simultaneous, you know, because as the train is moving, you know, the light waves begin to propagate from here towards her. So you see these blue arcs over here? So the light waves begin to propagate to the left over here, and the light waves begin to propagate to the right. So Marvis, what happens is that she's going to see the front door open first, because the blue wave has hit her in the head right now, so she sees the front door opening. But the back door has not, the information from the back door has not reached her yet. Okay? So according to her, the front door opens first and the back door opens later, because she's moving towards the front. Okay? So the notion of simultaneity is no longer an absolute, it's relative. Okay? This is another consequence of special relativity. Okay, another consequence is the notion of additional velocities. You know, I mentioned that one of the postulates of Einstein is that the speed of light in the vacuum is the same for every frame of reference. So, for example, if I have a flashlight and I shine towards the wall, the photons are going to hit the wall at the speed of light. The velocity of the photon is not going to change. It's going to be moving at the speed of light. But let's suppose that the wall moves away from me at the speed of light. So naively, you would say, okay, if the wall is moving away from me at the speed of light, then this laser beam will never reach the wall because the wall is getting away, it's moving away from the source. But Einstein said no, the velocity of light is always an invariant. So what happens is that the photons are going to hit the wall despite the fact that the wall is moving away, and the photons will hit the wall at the speed of light. But what happens is that the frequency of that light is going to be 0 due to the Doppler effect. So when the photons hit the wall that is moving away at the speed of light away from me, the photons will hit the wall, but the frequency will be 0. But the velocity will still be the speed of light. And conversely, if I have a wall that is moving towards me at the speed of light, the photons will hit the wall again at the speed of light, but the frequency due to the Doppler effect is going to be infinite. Okay? So, I mean, this is very, very subtle. Okay? So therefore, the notion of addition of velocities, you cannot add velocities naively, you know, because for example, this modify addition rule, this plus with a circle, is a modify addition rule. Okay, so let's suppose that we ignore the denominator here. So the naive addition of velocity is you just add the velocities, you know. But in relativity, you have to take into account the special relativistic effects that are going to modify this composition law of addition of velocities. So you have to include a denominator given by this expression over here. So what happens when v1 equals to the speed of light, which is the velocity of the photons? Let's suppose that v2 also equals to the speed of light. Let's suppose that the wall is moving towards me at the speed of light. So if you add them naively, you'll get twice the speed of light. But if you take into account this key denominator, due to the special relativistic effects, then when you do this algebra, you'll get that this composition law will give you the speed of light. Okay? So this is like a group composition law, which gives you always the sum of velocity will give you the speed of light. Again, if you are moving away instead of towards me, then you just change the sign for a minus here. You will change a sign for a minus here. Here you'll change a sign for a minus, and here you'll change the signs for a minus, and you'll get that the difference, the modified difference, will give you always the speed of light. Okay? Does this make any sense? Yeah. Okay, there's Sudarshan. Okay, now I'm going to talk about tachyons. So tachyons were postulated by George Sudarshan. You know, he was from India. He was from Kerala, and his office was across mine in Texas. He was a very wise Indian scientist, and he's the one who proposed the idea of tachyons. You know. So tachyons are hypothetical particles that can travel faster than light, and these particles could have been created at the beginning of the universe. Okay, so let me just. I didn't have the chance, but I guess I will, because I'm going to talk about this. If you have a massive object, you can always accelerate it to the speed of light, but in order to do that, we need an infinite amount of energy. Because you're going to have that the effective mass of an object is going to be given by the rest mass of the object times a factor that involves the Lorentz dilation factor, which depends on the velocity. Okay? So you're going to have the rest mass of the object, and then you're going to have the Lorentz factor over here. Okay, so if you have an object whose rest mass is not zero, if you are accelerated to the speed of light, when the velocity becomes the speed of light, this becomes zero. When you divide by zero, you're going to get infinity. So what happens is the effective mass will be infinite. It means that it will take you an infinite amount of energy to accelerate a massive object to the speed of light. Now the photons, by definition, they are moving at the speed of light because the rest mass, quote unquote, is zero. So it means a photon is never at rest because its mass is zero. So it's already moving at the speed of light. So you don't need to accelerate the photon because it's already moving at the speed of light. Now Sudarshan proposed the idea, what happens if the velocity is actually greater than the speed of light? Okay, so what happens here, then in that case, you'll get an imaginary number here. Okay, so what happens is you're going to have, you can always rewrite this expression in terms of, you're going to have a factor of minus I. Remember, I is the square root of minus 1. Okay, so I can just rewrite this expression as minus I n sub 0, and then I'm just going to flip the order. I'm going to have the order in which I write my square root. I have not done anything new. I'm just rewritten, this expression in this way, by flipping the order of my terms here. So now, okay, can I? Yeah, I think maybe I can draw something here. Okay. So Sudarshan proposed the idea, since he was from India, so he assumed, let's suppose that on the other side of the Himalayan mountains, there were people who, where tachyons live, So I'm going to plot the Lorentz factor as a function of velocity. Okay. So when the velocity is 0, I'm going to have a 1 here. And when the velocity reaches the speed of light, I'm going to have, the curve blows up. Okay? So this is when I reach the speed of light. And then what I'm going to do is I'm going to plot the same function, but by switching the order of these terms here. Remember, I'm going to plot this function also. This square with the order reversed. So what I'm going to have is I'm going to have a curve that looks like this. Okay? Like that. Okay? So when the velocity is infinite, well, this will go obviously, eventually will go to 0, actually. To be more correct, the asymptote goes like this, I'm sorry. Okay? Okay, it goes like that. Okay? And so imagine these are the Himalayas. Okay? So ordinary particles, are confined in this region. And tachyons, this is where tachyons live. Tachyons live in this region. Okay? Now, there's something very interesting. If you look at this expression over here, if you increase the velocity, this graph decreases and goes to 0. So what is the physical implication? Is that if you try to push a tachyon, if you try to accelerate the tachyon, it slows down, and vice versa. If you try to slow a tachyon, the graph increases. So if you try to slow a tachyon, it speeds up. And if you try to speed a tachyon, it slows down, which is completely counterintuitive. But the way to understand this is just by looking at the red line over here. So when B increases, the curve goes down. So this means that if you try to push a tachyon, it's going to slow down, and vice versa. If you try to pull a tachyon towards you, if you try to decrease its velocity, it speeds up. It has to do with the effective mass. And remember, the tachyon, they have imaginary mass due to this I factor. The tachyon has the mass square is less than 0. So it means that the mass is imaginary. Okay? So the fact that because the mass is imaginary, you have this strange phenomenon. Okay? Some of you have heard about tachyons before, I'm sure. Yeah. Okay. Okay. So let me. Okay. There's another consequence of relativity is the Doppler effect. Due to the time dilation, what happens? Let me go back. This is a. Sorry. Okay. This is the Earth. Going around the sun. Okay. This is us going around the sun. So due to the time dilation factor, moving clocks tend to tick slower than a clock at rest. And because moving clocks tend to tick slower, the frequency that we will observe is blue shifted. And vice versa, from our point of view, the sun is the one that is moving around us. Actually, I should have pointed in this direction. The sun is the one that is revolving around us. So due to this time dilation effect, the fact that moving clocks tick slower, in this case, we will experience a red shift. Here we experience the blue shift. So the Doppler effect is, this Doppler effect will not occur in classical mechanics because there's a transverse notion relative to the source of the light. So due to the time dilation effect, you are going to have this Doppler effect due to the circular motion. And essentially it has to do with the time dilation.
Oh,
yes, yeah.
Do you actually call that a Doppler effect?
It's a relativistic Doppler effect.
Okay.
Due to the time dilation. Due to the fact that the rate at which clocks tick vary in one frame of reference to the other. So that means that the frequencies also vary from one frame to the other. And this is why there's a blue shift or a red shift.
I also wondered, there's no violation of energy conservation in that?
No. Well, I mean, because you have to take into account that there's energy going around the sun. So we, you have to impart energy to the observer. Okay? Okay? So when you look at the total energy involved, the energy of the photons and the energy of the observer, of course the sun is going to lose energy because it's losing mass. So once you're emitting photons, you're right, the mass is losing energy, yeah, you're right. Okay, that's a good question. Okay, can I go for? Yeah, okay. Okay, so this is the, okay, you see the problem, because I have a PDF file, I cannot, I had a nice visual video of this, but because I cannot show the actual motion of the video, but this is also another very interesting phenomenon. If you have, for example, a sphere, okay, if you have an observer, okay, moving like this, for example, at a very high velocity, because this actually was a picture, but anyway, if you're moving like at a very high velocity, due to the length contraction, the actual shape of the sphere is going to deform. So the sphere is going to contract along the longitudinal motion. Okay, so this is actually what really happens. However, as we observers will never notice that, because due to an optical effect. Okay, so the visual appearance of the sphere will appear always to be a sphere, but in reality, the sphere is actually contracting. You know? And this is called the Perelman effect. And the reason the sphere appears as an optical illusion is spherical, despite the fact it's actually contracting, has to do with the fact that the light emitted from points that are closer to our eyes arrive to our eyes earlier than the light that is emitted from points further from us. So this is called a differential time lag effect. And due to this differential time lag effect, because what we see is all the photons coming from all the points of the sphere, and some points are closer to us than other points. So the light reaches our eyes at different times. So this creates this visual appearance that the sphere remains spherical, but in reality it's contracted. So the nice picture is that when you keep increasing the velocity, you're going to see the sphere on the left contract. And this sphere over here actually begins to rotate. Okay, so when you go to YouTube, I'm sure if you Google this effect, and you'll be able to see very nice images of how objects appear when they are moving very, very fast to the close of light, how they appear as they approach to us, they appear elongated, as they recede from us, they appear contracted, and as they pass by us, well, you have this effect. Okay, so let me. Okay, so this is the mass-energy relation that Einstein found. So when he wrote that energy equals to mc squared, by m, he means the mass, the effective mass, because remember, the rest mass is m sub 0, and m is the effective mass due to this relativistic factor of gamma. Okay? Because gamma is greater than 1, so the combination of gamma times m sub 0 is what you call m. Okay? So by m, you mean the mass due, at that moment, when the particle has the velocity v. So when the velocity of the particle is v relative to us, it has this energy content. This is the energy content of a massive object that is moving with respect to us at the velocity of v. Where m sub 0 is the mass of the object at rest, and gamma is the dilation factor associated to that velocity. Okay? So this is the energy content of an object. Of course, if you have a mass equal to 0, okay, in that case you have to invoke quantum mechanics, because when you have a massless particle, you have to invoke the wave-particle duality, and the energy content of a photon, when you invoke the wave-particle duality, if the photon is a wave, then you talk about a frequency, and then you need to introduce the Planck constant, where now the energy is given by the Planck constant times the frequency of the light of your wave. So in that case, you have to also invoke quantum mechanics when we're dealing with massless particles. Okay. Now, let's space travel under constant acceleration. Okay, so let's suppose that you have a very sophisticated device. Imagine that you can convert, you have a rocket and you use for fuel matter-antimatter propulsion. So, so matter and antimatter annihilate, and are going to propel your rocket all the way for a very, very, very long time. So let's suppose that you have a rocket that is continuously accelerating. Okay, continuously, at every moment it's accelerating. In that case, when you want to plot the relationship between the time that an observer on Earth experiences compared to the time that the person inside the rocket experiences, they're going to be related by it's actually a hyperbolic function. So let's suppose this is the time that the people on Earth observe is going to be proportional to a hyperbolic sine times the acceleration of the rocket. Let's suppose that we want to choose a rocket that accelerates at the acceleration of gravity, that we are all familiar with because we experience it every single moment of our lives. So g, is the acceleration of the surface of the Earth. Okay, and then tau is the time that the observer inside the rocket experiences. Okay, so when you plot this graph, remember that the hyperbolic function looks like this. The hyperbolic function, remember, the hyperbolic function is an exponential, minus the exponential divided by 2. So when the time, so essentially it's an exponential because for very large times you have a decaying exponential. So the first exponential wins. So you're going to have a curve that looks like this. So this is what you have here. You see this shape. This looks like an exponential curve. If you flip it this way. So what happens at the beginning of the Earth over here, you have the round trip time in the traveler's years, and over here you have the round trip time in Earth years. Okay, because of course you want to accelerate for half of your time, and you want to decelerate for half of your time in order to go back, because you cannot continue accelerating forever because you'll never reach the planet. You're going to crash against the planet. So if your travel time is 28 years, for example, you would like to accelerate for 14 years, and then you would like to decelerate for 14 years and reach your planet or your galaxy, and then you can come back. Okay, so over here on the left is the round trip time that the traveler experiences in his years. On the right is the round trip time in Earth years. Okay, and here is the distance in light years. Okay, this is the edge of the universe, about 10 to the 10 light years, which is what is like the Hubble radius. It's like 10 to the 28 centimeters. More or less, it's like the Hubble radius of the Earth. Okay, so what happens? Okay, at the beginning, there's not much difference between. Oh, you receive a message. What do I do?
Nothing.
It will go by itself.
Yeah.
Okay. So what happens at the beginning? This is like a straight line. There's not much difference between the traveler's time and the Earth time. But as you begin to keep accelerating, you're going to see a difference. And for example, where's the Andromeda Galaxy? Right here. The Andromeda Galaxy, if I remember, is about 2 million light years away, something like that. Okay. So remember, you can reach the Andromeda Galaxy in. Is that 90 years? Okay. So in 90 years.
50.
Or 95 years, you reach Andromeda Galaxy. But for us, look, it takes 10 to the 9 years. Okay. and then you can reach the age of the universe in 100 years, and of course round trip time, okay, and come back. You want to come back, so after 100 years you'll be able to reach the edge of the universe and come back. But for the people on the Earth, they'll be 10 billion years old, okay. So here you have a continuous acceleration, so that means that the velocity is continuously changing, okay. So you have this time dilation factor which is continuous. It's like having a continuous series of Lorentz transformations, if you want to do it that way. Okay. And then over here, I don't know, is this a UFO? I don't know what the hell it is. Anyway, but of course, in order to have the propulsion involved, it's humongous. I forgot how much energy you need. It's a humongous amount of energy that we don't have access to. Since Professor Eckhard is interested in wind energy, I don't think you can use this with a wind turbine or solar energy. Anyway, okay. So now let me talk briefly about general relativity. How much time do I have here?
Yeah, another 7 minutes.
Don't I get a time dilation?
But we need. There will be very interesting questions at the end. The students need to have some time for that.
I see. Okay. So 10 years after special relativity, Einstein suggested that gravity is not a force, but that gravity is due to the curvature of space-time. So you can imagine the Earth curving the space-time surrounding it, distorted the space-time. So if you have a point mass over here, due to the distortion of space-time, it's going to roll down towards the Earth, and this will mimic the effect of gravity. So this is the Einstein field equations, including the cosmological constant. So over here I have the Ricci tensor, I have the space-time metric, I have the curvature scalar, and in the right-hand side I have the stress-energy tensor. So physically this means that the presence of matter on the right-hand side is going to curve space-time, and space-time will tell matter how to move, like Wheeler used to say. Matter is going to curve space-time. The presence of mass, the Earth has mass, is going to distort the space-time, and is going to tell a point mass over here how to move. Okay, so matter tells space-time how to curve, and in turn space-time tells matter how to move. Okay? So these are the field equations. So if you are in 4 dimension, the Ricci tensor is a symmetric tensor, and we will have 10 independent components. So in reality, when you write these equations down, you're going to have 10 differential equations. They're going to be non-linear partial differential equations. And the solutions, the exact solutions of Einstein's equations, there's only a very limited number of them. I think there's a book that has written down all the known solutions of Einstein's equations, but there are only actually very few that we can solve exactly, because they are non-linear partial differential equations and they are all coupled. So it's a very, very complicated system of differential equations. And then, so here they got the black hole. So one of the solutions, I guess next week I'll be talking about the Schwarzschild metric. I think the Schwarzschild in 1916 found a solution of Einstein's equations that where you have a source at the center and you have what you call the event horizon. And this actually, I don't think that this is actually, well, I think this is an artistic depiction of a black hole swallowing a star. But actually now with the James Webb Space Telescope, we are witnessing so many cosmological events that have never been seen before. Like this, I guess this is an artist's rendition of an actual event. So over here, of course, as matter begins to swirl, then there's some production of jets due to X-ray production. And somebody told me that nobody knows exactly yet how these jets are produced. It's still an unanswered question. This is what somebody told me. Okay, so this is about black hole thermodynamics. Okay, so the connection between entropy and black holes stems from a conversation that Wheeler had in Princeton many years ago when they were having tea, and he gave a student, Bekenstein, a very simple question. Well, it was not that simple. That if you had a cup of tea or a cup of coffee, what will happen to the entropy of the cup of coffee or cup of tea if you threw the cup inside a black hole? So it appears to violate the second law of thermodynamics, because of course if the cup of coffee disappears and we don't have access to the cup of coffee, it will mean that there has been a decrease in the production of entropy. So if the entropy decreases, that will be a violation of the second law of thermodynamics. So Bekenstein thought about this problem. So he didn't realize that if you throw a cup of coffee into the black hole, if you feed the black hole with a hot cup of coffee, the energy content of that cup of coffee is going to increase the mass of the black hole. And if you increase the mass of the black hole, the size of the event horizon is going to increase. And the size of the area of the event horizon is going to increase. So this is when he came up with the idea that the entropy of the black hole has to be intimately connected with the area of the horizon. Okay, so that's where he came with the idea, the Bekenstein entropy. So here, of course, I'm using these units where the h bar and the c and are equal to 1. You know. So over here, this is the Boltzmann constant. You remember the Boltzmann constant has the same units as entropy. So the ratio of this area, the area of the horizon compared to the Planck length. Remember, this is the Planck length that involves the fundamental constants in physics, the strength of the gravitational interaction, the Planck constant, which is what rules quantum mechanics, the speed of light. So this Planck length has these three fundamental constants of physics in it. And then when you include the Boltzmann constant, so in these equations you are dealing with the fundamental constants in physics. So you are dealing with a very deep interplay between quantum mechanics and relativity.
So one more minute.
One more minute. Okay. So the Hawking radiation. Okay. So here I set my fundamental constants to 1. So what happens? For many years, people thought that black holes, once they were formed, they stay fixed. But Hawking, when he studied quantum field theory and a curved background, he realized that the vacuum is not really empty. There's a continuous production of particles, virtual particles. So you have electrons and positrons that are created and annihilated with each other. So the positron falls into the black hole, and the positron has negative energy. So that means that the black hole is losing mass, and you emit a particle outwards. And this has to do with the so-called information paradox, that if a black hole is going to radiate, it's going to emit particles, and the black hole is going to evaporate. So if the black hole evaporates, that means that information is lost. So all the information that went into the creation of the black hole, if the black hole were to evaporate, the information will disappear. And this would be a violation of the principle of unitarity in quantum mechanics, that the information cannot be destroyed. So many, many years people have been trying to resolve the black hole information paradox, and the latest development are related to the notion that the creation of wormholes. This is called the Einstein-Rosen equals Einstein-Podolsky-Rosen paradox. So Susskind in Stanford and Juan Martín Maldacena in Princeton came up with the idea that maybe in order to resolve the paradox, it could be resolved through the creation of wormholes and the notion of entanglement. So the information of the black hole actually is not, in other words, the information of the black hole is not destroyed, but what happens is that it slowly leaks out of the black hole. And it leaks out through the emission of these particles, but not only through the emission, but most importantly, through the correlations and the entanglement among all these particles. It is the entanglement between all these particles that carry the information that was stored in the black hole. So in a certain way, they believe that the information is not destroyed, but it's the entanglement between particles that actually process the information. And that entanglement occurs through wormholes. It's the wormholes that induce the entanglement. If you destroy the entanglement, the wormhole disappears. Okay. Anyway, so okay. Thank you so much. Thank you so much.